Today we will discuss p block elements. As we know, periodic table is divided into 4 blocks: S block, P block, and D block and F block. So for our first semester syllabus is p block elements. What are p block elements? First we have to know that p block elements are nothing but the differentiating electron enters into p orbital. The elements in which differentiating electron enters into p orbitals are called as p block elements. So p block, as p orbital contains maximum, p orbital can accommodate maximum number of electrons are 6. So p block contains only 6 groups. They are nothing but 3rd A, 4th A, 5th A, 6th A and 7th A and 8th A. We can call them as 13 to 18 groups. We can observe this in periodic table, that is they are placed right side of the periodic table, that is from boron family to 0 group elements or 8th A group elements. So we are confined to 3rd, 4th and 5th group in first semester syllabus. Let us discuss before going to details of 3rd, 4th and 5th group elements. We have to know some general properties of the group, 3rd, 4th and 5th groups. We have to know the electronic configuration, oxidation states, allotropy, melting and boiling points, catenation, electronegativity, inert pair effect and metallic and non-metallic nature. So electronic configuration of p block elements varies from Ns2Np1 to Ns2Np6. Coming to the oxidation states, any p block element maximum number of oxidation state it can show is equal to the number of valence electrons in it. Besides that, it shows some additional oxidation states also. We will see in detail in different groups. Allotropy is nothing but the elements which exhibits more than one physical forms. This we can mostly observe in 4th group elements, that is carbon and silicon. Shows allotropic forms. Coming to melting and boiling points, regular trend in a group is nothing but melting and boiling points decreases, in a period it increases. Coming to catenation property, catenation is nothing but self linkage. For example, carbon can link with other carbon atoms to form long chains and rings. This property is called as catenation property. This is a 4th group elements, carbon and silicon, this is limited to. So this we will discuss in 4th group elements separately. As we know, electronegativity in group decreases from top to bottom. Coming to inert pair effect, this is related to the oxidation states, that is besides maximum number of oxidation state, it shows 2 units less oxidation state. They are stable in that oxidation state. As we move from top to bottom, the heavier elements are very stable in lower oxidation states than in higher oxidation states. This we will discuss in separately group wise. As we know, metallic and non-metallic metallic nature gradually decreases. Metallic nature gradually increases from top to bottom. Non-metallic nature decreases. So coming to chemical properties, for different compounds we have to study hydrides of 3rd group elements, 4th group elements, 5th group elements, that is compounds of an element with hydrogen are called as hydrides. When the compound combines with oxygen, they are called as oxides. When it combines with halogens, they are called halides. Oxyacids are nothing but when oxides dissolved in water forms oxyacids. So let us discuss about 3rd A group elements. 3rd A group elements are nothing but boron, aluminium, gallium, indium, thallium are called 3rd group elements. So coming to the physical properties, electronic configuration of 3rd group elements is nothing but Ns2Np1. From the electronic configuration, we can observe that 3 valence electrons are present in the outermost orbitals. So oxidation state and common oxidation state is +3. Due to inert pair effect, heavier elements shows only +1, they are stable in +1 oxidation state. So what is inert pair effect? Inert pair effect is nothing but దీన్నే మనం జడ ఎలక్ట్రాన్ జంట ప్రభావం అని కూడా అంటారు. Inert pair effect is nothing but reluctance of s electrons to participate in the chemical bonding. This is due to, as we go from top to bottom, atomic size increases. Due to this poor screening effect, s electrons are more and of nucleus. Due to that, s electrons reluctant to participate in the bonding. So heavier in case of third group elements. Thallium is stable in its +1 oxidation state in its compounds more than trivalent state +3. So this is called inert pair effect. What is important in inert pair effect in the entrance point of view is nothing but, so here thallium +1 oxidation state compounds are ionic in nature and trivalent oxidation state compounds are covalent in nature. So this we have to remember, this is the point. Only heavier elements, there is a slight progress in the inert pair, due to inert pair effect they show they are very stable in the lower oxidation states. Coming to boron hydrides. So what is there in our first semester syllabus is important compounds of the third group elements, fourth group elements and fifth group elements are discussed in the first semester. So coming to the important compounds of the boron. So boron hydrides are very, very important. The compounds of hydrogen with boron are called as boranes or boron hydrides. Aluminium with hydrogen are called as aluminium hydrides or allenes. So, but the important point is nothing but boron hydride, borane very, very important. These borane depending upon the molecular formula and stability. So, they are classified into two types: boranes with molecular formula BnHn+4, archenoboranes with the molecular formula is very, very important because nearly 20 to 30 boranes are there. So, in BnHn+4, nidoboranes are stable boranes, archenoboranes are unstable boranes. So, in nidoboranes the starting compound is B2H6 diborane, it is called as. Next one is pentaborane. In archenoboranes also, if you observe from the boranes from the picture, B4H10 and B5H11 under important, the prefix diborane, triborane, pentaborane, prefix indicates the number of boron atoms, the suffix number. So, while naming pent11, we have to mention the number of hydrogen atoms at the last, that is pentaborane 9. It indicates it comes under nidoboranes, that is BnHn+4. So 11 indicates the pentaborane 11. That 11 indicates the number of hydrogen atoms. So naming of the boranes is also very, very important. Diborane and higher borane, in higher boranes, pentaborane 9 and B4H10 are in our syllabus. So we have to discuss the structures of those compounds. So out of all boranes, diborane is very, very important because of its uses also. That is, it is used as a reducing agent and hydrocarbons and carbonyl compounds through hydroboration methods. So many uses are there for diborane. So it is very, very important and its structure is also very interesting. First we will know the preparation methods of diborane. So coming to the preparation method, the lithium aluminium hydride or sodium borohydride, reduction of the boron trihalides will give diborane in large quantities also. So coming to the chemical properties of diborane, it is very toxic and poisonous gas. It readily reacts with oxygen. In air it explodes. With oxygen it burns with oxygen and gives boron trioxide. Thermic reaction, enormous amount of energy is released. So along with that we are seeing here this reactions with diborane reacts with ammonia in 1:2 ratio at low temperatures. This temperature very, very important. So temperature we have to see here, 1:2 ratio when diborane reacts with ammonia, the addition product is formed, that is diammoniate of diborane. So but when high temperatures in 1:2 important compound, that is borazole B3N3 is also called as inorganic benzene. So this is formed at high temperatures. Diborane when reacts with ammonia, we have to take ammonia, we will get one polymeric compound boron nitride which has similar structure like graphite. So in diborane chemical properties we have to concentrate more on at different temperatures. These three are very important: addition product and formation of boron nitride polymeric structure. So very, very important is structural elucidation of diborane. Just like B2H6 and C2H6, where carbon belongs to fourth group, boron belongs to third group. It has less number of electrons for bond formation. A structure like diborane, what we should observe is, Here the total number of electrons for bonding is 14 electrons, but in diborane the formula is B2H6. B2H6 boron has valence electrons, 2 borons totally 6 valence electrons. 6 plus 6 only 12 electrons are there. Electrons are less than to form expected number of covalent bonds. So then what will be the structure of diborane? Different studies shown the methylation reaction is only tetramethyl was formed during methylation reaction. Tetramethyl product, that is only 4 remaining 2 hydrogens cannot be replaced by the methylation reaction. So from electron diffraction studies it is known only 4 hydrogens lie in one plane, 1 hydrogen above the plane and 1 hydrogen below the plane. NMR studies also shown that all the 6 hydrogens are not identical. 4 hydrogens gave one type of signal, 2 hydrogens gave one type of signal. So from bond angles also we can observe that the bond lengths are different. These bonds are 4 there. So the bond length is nothing but 1.33 angstroms. Coming to these, when we see the structure carefully, so if we see the structure, this BH bond length is 1.19 angstroms, that is all BH bond lengths are not equal. So angles are also not equal. In between terminal the bond angle is 120 and between this BH bond angle is 83, we can observe it from the structure. So what we can say from this is, so we cannot have the structure like ethane. Delta scientists proposed the bridged structure, that is bridge like structure for diborane, where so in that 4 sp3 orbitals, 2 sp3 hybrid orbitals of each boron atom normally forms BH sigma. One has one vacant orbital, one vacant sp3 there, and one orbital is having the only single electron. So if we observe the structure, the half-filled sp3 and the hydrogen 1s orbital overlap, resulting in the formation of 3-centered 2-electron bond. So that is 3 కేంద్రకాలు 2 ఎలక్ట్రాన్ల బంధాన్ని ఏర్పరుస్తాయి. ఇందులోని వేకెంట్ లోని ఒక ఎలక్ట్రాన్ కలిగి ఉన్న ఆర్బిటాల్, హైడ్రోజన్ లోని 1s ఆర్బిటాల్, దట్ ఈస్ 3 కేంద్రకాలు 2 ఎలక్ట్రాన్లతో కూడిన ఓవర్లాపింగ్ అనేది జరుగుతుంది. దాని వలన ఒక బ్రిడ్జ్ బాండ్ అనేది ఏర్పడుతుంది. సో సెంటర్ లో హైడ్రోజన్ ఆటం అనేది ఉంటుంది. ఇలాంటి బంధాలను మనము 2 ఏర్పడతాయి. ఆ రకంగా 2 ఎలక్ట్రాన్ల కొరతను చూసాము. వేర్ దేర్ ఇస్ 2 electrons deficiency, that electron deficiency is compensated by the 2 bridge hydrogen bonds. So in this structure we are observing some banana bond like shape, banana shape like bond in the diborane. So why we are getting the shape like this? Okay, it is 3-centered 2-electron shape like this because this is because of repulsion between the 2 hydrogen nucleus la madhya vikarshanaల కారణంగా slightly the orbitals are slightly drifted away. So దాని వలన ఏమవుతుందంటే slightly drifted away in the middle. So we will get the shape like banana. We can call that those 2 bridged bonds as banana bonds అని కూడా అంటారు. In the examination point of view, what we have to mention, 2 boron atoms undergo 2 boron atoms undergo sp3 hybridations, normal sp3 s sigma bonds, remaining 2 electron bonds. How many 2-centered 2-electron bonds are there? How many 3-centered 2-electron bonds are there? We have to mention the bond angles. So terminal BH bond length is somewhat more than the bridged BH bond length. So this we have to mention in the examination point of view. Structure is very, very important. Coming to next, this is the overall structure, sp3 vacant and filled orbital. So next important compound of boron is nothing but N3H6. So by seeing the formula itself, we remember that it is just like benzene, that is C6H6. Instead of all carbon atoms, boron and nitrogen atoms are present in this. So diborane on heating with ammonia at high temperatures, we will get in 1:2 ratio, we will get borazole. So along with that, industrial scale of reaction we are observing here, lithium borohydride with ammonium chloride. By this method we can prepare large quantities. Coming to the structure, this is very, very important. Isoelectronic and isostructural with benzene, where boron and alternatively. If you see the picture here, atoms are arranged alternatively to each other. Hydrogens are present on each boron atom and nitrogen atom also. So what is the difference between benzene and here is alternatively boron and nitrogen atoms. There the pi bond is present between C double bond C, but here it is not exactly the pi bond between boron and nitrogen. The double bonds present, alternative double bonds present between the boron and nitrogen, just like similar to that of benzene. But the difference here is the pi bond in these compounds in borazole is, it is a orbital is present in boron and one filled orbital, that is low. The overlap of the orbitals, vacant orbital of boron and filled bonding is formed between boron and nitrogen in inorganic benzene. This is also volatile compound. So we can see the structure from the pictures. Coming to another most important compound, boron nitride, which is very hard material. It has many industrial applications, that is boron nitride. The preparation features, we will get the polymeric graphite. All the carbon atoms are arranged in each layer contains of hexagonal rings, planar hexagonal rings. Here each hexagonal planar ring contains boron and alternative arrangement of boron and nitrogen atoms. So what is the difference here is, just like that boron nitride is also boron nitride is a hard material. Moreover, if we observe the comparison between, so we can write the structure from the layer like structure it has sp2 hybridization. But the important thing here is, what are the differences from graphite is good conductor of electricity, because carbon valency is 4. There one electron, when carbon undergoes sp2 hybridization, one free electron, nitride is bad conductor of electricity. It is used as insulator, good insulator, because there are no free electrons in the structure. This point we have to remember, because normal properties and normal preparations we can read, but what are the specialities? When we are comparing it with graphite, we have to discuss what are the differences between. When we discuss that, when its structure is similar with the graphite, whether the properties are also similar with the graphite or not. And this is insulator, not like graphite. So next, coming to higher boranes are also important. Under higher boranes, tetraborane and pentaborane in our syllabus. If we observe the structure of tetraborane, preparation is very important. As usual, it can be prepared from, all the higher boranes are prepared by borane at different temperatures. We will get the mixture of higher boranes actually. By maintaining the temperature carefully, we will get tetraboranes, pentaboranes, other higher boranes. One more industrial preparation is also there for tetraborane, that is magnesium boride with HCl reaction. We will get the important point is again the structure of tetraboranes. Tetraborane, all the high terminal BH bonds and BHP bridged bonds. Along with that, higher boranes also contains one BB bond. In some cases, BB relation point of view, we have to touch these points. How many bonds? In all the higher boranes, boron atom undergoes sp3 hybridization, no doubt in that. So terminal bonds are present. How many BHB bonds are present? That is bridged bonds, 3-centered 2-electron bonds. So in tetraborane, 4 bridging BHB bonds are present, 1 BB bond, terminal BH bonds are present. This is important while writing the structure. Coming to pentaborane, preparation methods are, that is by heating diborane or at 200 to 250 degrees, we will get. Coming to the structure, again structures are important. Under boron compounds, for all the boron compounds, the structures are studied. It has BHB bonds, 2 BB bonds, and in pentaborane, 1 bridged BBB bond is present. So these are very important points we have to. So next is nothing but the very important topic is boron trihalides. Boron trihalides are nothing but the compounds of boron with halogens. Generally, it forms with the molecular formula BX3, where boron trifluoride, boron trichloride, boron tribromide, and boron triiodide. But the important thing is Lewis acids. Why they are acting as Lewis acids? We can get it from the structure. By observing the structure, Most configuration of boron is Ns2Np1. So hybridization. sp2 hybrid BF3, all 6 electrons are present in boron atom, one vacant orbital halides, not BBr3, Bi3, all are electron deficient compounds because one vacant orbital less than the number of valence orbitals. So they act as Lewis acids. Lewis acids means లూయి ఆమ్లాలు అంటే ఏంటి, ఎలక్ట్రాన్లను స్వీకరించగలిగిన కెపాసిటీ ఉన్నటువంటి వాటిని మనము లూయి ఎలక్ట్రాన్స్. Why they are accepting acidic character changes from BF3 to BBr3 is very important, because F3 to Bi3 in all the elements boron is common. On the electronegativity of halogen atom, fluorine is more electronegative and iodine is less electronegative. So what we will think, acidic character decreases down the group because fluorine more electron. 3 is weak acid. What is the reason? The Lewis acidic character decreases down the group, decreases down from BF3 to BBr3. What is the reason? The reason for this is very important. Why? Right domination point of view, they are asking that why acidic character, unexpected acidic character for boron trihalides, that is from BF3 to BBr3. Then in boron, what we are observing here, we can see the orbitals. In boron, one vacant orbital is there. Halogen atoms also have one filled orbital. In fluorine, 2 electrons are there in fluorine, but 2p orbital of fluorine. And in chlorine, if we observe, 2 electrons are there in 4p orbitals. So in fluorine, the filled orbital of fluorine overlaps with vacant, resulting in the formation of some double bonded character, like bond is formed. So double bond character is developed. Due to that double bond character, electron deficiency on the boron atom reduces. So fluorine back donates electrons to boron atom. దాని వలన ఏమవుతుంది, తగ్గిపోతుంది. ఫ్లోరిన్ బోరాన్ కి ఎలక్ట్రాన్లను ఇవ్వడం వలన ఆర్బిటాల్ ఆఫ్ బోరాన్ electron deficiency reduced. But what is happening in chlorine BCl3 and BBr3? BCl3 and BBr3, if we observe, the sizes of the atom, the overlap, effective overlapping will not take place in BCl3 and BBr3 because the difference in the atomic orbital's size. So automatically the back bonding capacity increases from BF3 to BBr3. దీని వల్ల ఏమవుతుంది, BBr3 అనేది స్ట్రాంగ్, it has more capability to accept the number of electrons. దాని వలన acidic character increases from BF3 to BBr3. So this is very important about borons. So next we will discuss 4th A group elements. As we know, carbon, silicon, general electronic configuration elements is Ns2Np2. Number of valence electrons are nothing but plus 4 electrons. So from the valence electrons, we can say the oxidation state, maximum oxidation state is +4, along with that +2, and remaining even carbon can exist negative oxidation state in carbides also. Carbon and silicon are remaining as the metallic character increases down the group. Germanium is a metalloid, tin and lead are metals. So next here we have to touch the important property, that is catenation. Long chains and rings is called as catenation. Why carbon has more tendency, silicon catenation power is limited to only 8, but carbon has high capacity of forming long. That is why many carbon compounds we know. So why carbon is able to show high catenation power is because of its carbon-carbon bond strength. Carbon-carbon bond strength is 297 kilojoules per mole. So because of this bond energy, they show catenation capability decreases down the group. Carbon and silicon, we can see the many, this catenation power is more and more in carbon. It has unique ability to form pp multiple bond C and C triple bond C it can form, and also C double bond O, multiple bonding nature. P multiple bonding nature. It exhibits many allotropic forms. As we know very well that it has crystalline forms. Crystalline allotropic forms, graphite and diamond are very important. Along with that, we know recently fullerenes are also there. That is also one allotropic forms of carbon. Along with that, many amorphous forms are also there. That is charcoal, coke, These are amorphous forms of allotropic forms of carbon. So coming to chemical properties, hydrides of silicon are very important. We call them as silane, dioxide, carbon monoxide, silics. Coming to the halides, they form halides with the formula MX4. It's PbCl2 also, which is stable oxidation state. Coming to the important topics in this fourth group elements are and silicones. Coming to the carbides, carbides are nothing but compounds, that is కార్బన్ ఆటం కన్నా తక్కువ రుణ విద్యుదాత్మకత కలిగిన మూల అయానిక్ కార్బైడ్స్, కోవలెంట్ కార్బైడ్స్. ఇన్ మెటాలిక్ కార్బైడ్స్ ఓన్లీ ఇంటర్స్టిషియల్ కార్బైడ్స్ విల్ కమ్, దట్ ఈస్ అయానిక కార్బైడ్లు, సంయోజనీయ కార్బైడ్లు మరియు అల్పాంతర కార్బైడ్లు అని టైప్ ఆఫ్ బాండింగ్. అవి వాటి మధ్య ఉన్న ఎలక్ట్రోనెగటివిటీ డిఫరెన్స్ కానీ అవి ఏర్పరిచే బంధ స్వభావాన్ని బట్టి దే ఆర్ క్లాసిఫైడ్ ఇంటూ దీస్ 4 types. So first we will see ionic carbides. In ionic carbides, again they are classified into methanides. This is very very important academic syllabus also, because ionic carbides they are further classified into methanides, hydrolysis products. Hydrolysis products ante aluminium carbide jala vishleshana meeda on hydrolysis aluminium carbide will give methane as one of the products. So they are called as methanides. Even beryllium carbide. Coming to acetylides, methanides contain C-4 units, C3-4 units. Acetylides contain C2-2 units, that is calcium carbide. We know very well this calcium carbide is used for artificial fruit ripening along with lithium carbide and silver carbide. These on hydrolysis will give acetylene as one of the products. That is why they are called as acetylides. Next, allylides. Magnesium carbide on hydrolysis. Idi jala vishleshana meeda allyl. These type of carbides are called as allylides. So coming to covalent carbides, silicon carbide is very very important, because as we know this is called as carborundum. It can be prepared from by reacting silicon oxide with coke at high temperatures. We will get this silicon carbide, very very hard material. It is used as abrasive for cutting tools and those sharpening tools. We will use this silicon carbide. It has 3-dimensional joint polymeric structure. Next, interstitial carbides. Interstitial carbides, how it will be prepared? Ivi alpantara carbidelu antaru. Name lone undi. When the carbon atom enters the interstitial sites of the metal, interstitial carbides are formed. ఎక్కడైతే స్ఫటికం యొక్క ఖాళీ స్థలాల మధ్యలోకి కార్బన్ ఆటం చేరుతుందో దాని ద్వారా ఇంటర్స్టిషియల్ కార్బైడ్స్ ఏర్పడతాయి. ద బెస్ట్ ఎగ్జాంపుల్స్ అండర్ దిస్ ఆర్ Fe3C, cementite, which is very very, these interstitial carbides have very industrial applications చాలా ఉన్నాయి వీటికి. Fe3C cementite, it is important constituent of steel. టంగ్స్టన్ కార్బైడ్, టాంటలం కార్బైడ్ ను తీసుకున్నట్టయితే దీనికి మెల్టింగ్ పాయింట్ చాలా చాలా ఎక్కువగా ఉంటుంది అండ్ వెరీ లైట్ వెయిట్ లో ఉంటుంది. సో దీన్ని చాలా రకాలుగా మనకు ఇండస్ట్రియల్ అప్లికేషన్స్ పరిశ్రమల్లో కానీ ఎలా ఇన్ ద ప్రిపరేషన్ ఆఫ్ సమ్ మెటీరియల్స్ లో దీన్ని యూజ్ చేస్తూ ఉంటారు. టంగ్స్టన్ కార్బైడ్, ఇఫ్ యూ అబ్జర్వ్ ద అప్లికేషన్స్, ప్రిపరేషన్ ఆఫ్ ద మెటీరియల్స్, tungsten carbide is also light in weight and very hard material it is. If you see the structures, silicon carbide, boron carbide and calcium carbide, tungsten carbide, out of this tungsten carbide is very very hard and it has wide industrial applications. So silicon carbide is used as an abrasive. So calcium carbide, it is not that much hard, it is used as a in powder state, it is used as for artificial ripening of fruits. Coming to silicones, one more important topic of the fourth group is silicones. What are silicones? Silicones anagane the organosilicon polymers which are having SiO-Si linkages. The general formula is R2SiO. So if you observe the structure of silicones, SiO-Si linkages with alkyl groups. By seeing the structure, we can say they are very very hard chemical inertness. Due to their chemical inertness and high thermal stability, silicones are having very high industrial applications. So types of silicones. Silicones are 4 types basically: long chain silicones, cyclic silicones, cross linked silicones, hexaalkyl silicones. So for all the silicones, the starting materials are nothing but alkyl or aryl chlorosilanes are the starting materials. So there are 3 preparations for these. These are the starting materials. Alkyl or aryl silanes are the starting materials for silicones. So these are linear silicones. These are the structures of cyclic silicones. These are nothing but this is cross-linked silicones. They are very hard depending upon the number of silicone units, SiO, Si units, R2 SiO units. They are used as silicone rubbers, greases, resins and water repellent films. They are water repellent because of the presence of non-polar groups present in silicones. We can observe it from the structure, that is non-polar alkyl groups. They are water repellent in nature. So depending upon the number of units present in the silicones, they are classified into silicone fluids, rubbers, greases and resins. Silicones having 20 to 500 units are used as silicone fluids. Having more number, 6000 to 7000 units, they are used as silicone greases, because as the number of silicone units increases, their melting and boiling points and viscosity also increases. So silicones are used as greases, and resins are they can be used as resins. Silicone rubbers, because all the silicones have elastic property, so they are used as rubbers. So these are the materials formed from silicone. Coming to 50A group elements, it's aluminum and bismuth are 5th group elements. Again, the electronic configuration is Ns2 Np3, that is 5 valence electrons. So here the important is nothing but here nitrogen is a gas, remaining all are solids. Coming to oxidation state, +3 and +5 are the important oxidation state. In this, nitrogen cannot extend due to non-availability of d orbitals. It cannot extend its valency more than 3. So coming to atomicity, nitrogen exists as dimer N2, phosphorus P4 units. So these are the important properties. So next, chemical properties, nitrides, hydrazine and hydroxylamine phosphazines we have to study in the 5th group. Nitrates already we have seen boron nitride, but again that is compounds of nitrogen with less electronegative element than the nitrogen are called as nitrides. So nitrides, ionic nitrides, again depending upon the nature of the bonding, ionic nitrides, covalent nitrides and interstitial nitrides. Just like carbides, they are also classified into 3 types. So out of which boron nitride has got very important applications. So here we can see the preparations of different nitrides, calcium nitride and aluminum nitride, directly combining metal with the nitrogen, or reduction of oxides or chlorides with nitrogen in presence of coke we can prepare. Coming to phosphonitrile halides, these are also called as phosphazines. Phosphazines are nothing but phosphonitrile halides having the general formula PnX2 taken in. Actually X can be fluorine, chlorine, bromine, methyl, or it can be some phenyl groups also, but PnCl2 taken in has wide important industrial application. So we can take phosphonitrile chlorides only. So what is important in the phosphazines is the structure of phosphazines. Alternate phosphorus and nitrogen atoms are arranged alternatively in all the phosphazines. Halogen atom, that is chlorine atoms, are present on phosphorus. So while studying about the structure, the important point is nothing but phosphorus is present in +5 oxidation state, nitrogen is present in X bits +3 oxidation state in phosphazines. So higher phosphazines shows some boat conformers and chair conformers also. Why phosphazines are important are they are fireproof and waterproof. They can be used as fireproof and waterproof materials. In seeing the preparation methods, Raschig's process is very important. This can be prepared by oxidation of ammonia in presence of sodium hypochlorite, we can prepare hydrazine. This is hydroxylamine. If we see the preparation of hydroxylamine, we can prepare it from the reduction of nitric oxide, hydroxylamine. This is NH2OH is the formula of hydroxylamine. Hydrazine is used as important reducing agent. Hydroxylamine also to hydrazine and hydroxylamine both are very important to characterize the organic compounds, that is carbonyls and the acids. So these two are important. So these are the important topics in fifth group, that is phosphazines, industrial applications, waterproof and fireproof materials they are used as. Hydrazine and hydroxylamine అవి ఆర్గానిక్ కెమిస్ట్రీలో మనకు రెడ్యూసింగ్ అండ్ హైడ్రాక్సిలమైన్ ఆక్సిడైజింగ్ ఏజెంట్గా కూడా ఉపయోగపడుతుంది. కొన్ని కర్బన సమ్మేళనాలను క్యారెక్టరైజ్ చేయడానికి కూడా ఉపయోగపడతాయి. కాబట్టి ఈ మనం ఫిఫ్త్ గ్రూప్లో ఈ కాంపౌండ్స్ అన్నిటినీ కూడా ముఖ్యంగా కాన్సన్ట్రేట్ చేయాల్సినటువంటి అవసరం ఉంటుంది. సో ఆల్ దీస్ సెమిస్టర్ ఎగ్జామ్స్కి ఇంపార్టెంట్ క్వశ్చన్స్ వచ్చేసి మనం ఇంతవరకు ఏదైతే చదువుకున్నామో బోరాన్ ఫ్యామిలీలో ఫోర్త్ గ్రూప్లో వచ్చేసి ఫిఫ్త్ గ్రూప్లో వచ్చేసి ఆ కాంపౌండ్స్ అన్నిటి గురించి, అంటే డైబోరేన్ ప్రిపరేషన్ ప్రాపర్టీస్, కమింగ్ టు నైట్రైట్స్ ప్రిపరేషన్స్ అండ్ ప్రాపర్టీస్ అండ్ స్ట్రక్చర్స్. సో ఈ రకంగా ఫాస్ఫజీన్స్ అప్లికేషన్స్, ప్రిపరేషన్స్, ప్రాపర్టీస్ వీటన్నింటి మీద మనం కాన్సన్ట్రేట్ చేయాల్సి అవసరం ఉంటుంది. సో సిలికాన్స్, ఈవెన్ సిలికాన్ స్ట్రక్చర్ ఏంటి, సిలికాన్స్ అప్లికేషన్స్ ఏంటి, లీనియర్ సిలికాన్స్ ఏంటి, cyclic silicones, how to prepare, all these are important points in the semester exams. So with this entrance point of view లో వచ్చే క్వశ్చన్స్ కూడా మీరు ఇక్కడ చూడొచ్చు. సో ఏ రకమైనటువంటి బాండింగ్ అనేది ఉంటుంది, అప్లికేషన్స్ ఏంటి, వాట్ ఆర్ ద హైబ్రిడైజేషన్, type of bonds present in borazole and all those. So these are the important questions. So thank you very much.